Dear all, welcome to the second lecture on today by Sri R. Madhusudan Rao, Director, Urja Energy Private Limited, Hyderabad, on the topic Solar Thermal Applications for Industries. Now I request Sri R. Madhusudan Rao Garu to give a talk on solar thermal applications for industries. Thank you, sir. Over to you.
Thank you, sir. I have two presentations. One is generally solar thermal applications and on the cooling. That will be presentation. What will be mostly what we have done, and there are different applications in different industries. Some of those I have not covered in this presentation, but I will lay out a general framework of how to evaluate what is feasible, what is not feasible, rather than going much deeper into each technology. I will touch different types of technologies, but we'll try to give a more practical approach as to how industry evaluates these solutions. I hope that will bring some value instead of just telling about the technology. So, if you look at the peak oil theory, what we are looking at by many forecasts, if there are different forecasts.
Sir, your presentation is not coming. Share content.
Okay. Is it visible now?
Yeah, fine, coming.
Yeah. So there are different
fine.
estimates which basically point to the reduction in production of oil.
Sir, please start from the title, please, sir. Please, from title slide. We missed the first slide.
Yeah, this is the first slide. Then this is the next slide.
Yes, fine.
Okay. So the peak oil theory, which has been around for a few decades, people have been predicting that oil production will start declining. That has been there for quite some time. Everybody's been waiting for that, and it keeps moving it a bit. But the world oil production at some point will come down, and oil definitely is one of the major fuels that a lot of industries use. Many industries cannot use coal even if oil were not available because of the kind of production they do. For example, many food industries, people who manufacture your tomato ketchup, your let's say Lay's chips. So food industry would not use coal. Dairy will not use coal because of the kind of contamination, possibility of contamination that exists. So many of them these use oil. So this is where we see that there are possibilities for using solar thermal solutions, technologies. So in almost all cases, what we today or we've been seeing is solar thermal as a technology is considered post-installation. Right? During project phase, there have been very few projects who considered solar thermal during the project's implementation stage itself. But in many times when we talk to the industry, we are at a stage where the system is already running, the process is already going on, and then we have to retrofit it to it. So broadly, if you look at it, there are three areas where you can see this is possible to do. One is to generate steam itself. On the top left corner, you will see that the way many process industries are there is a central boiler, and that provides steam to different processes, steam or hot water, whatever. So we can generate at that stage itself where the input is given to the boiler, the steam, or is in parallel to the boiler. It can also be done where on the right side, if you see, we can apply it to just a specific process, in which case we have to integrate the solar field only to that process, or we can also use it for makeup water. Even though, so all the steam would be produced at 10 bar, and then there will be a pressure reduction valve to reduce the pressure. Let's say the last process requires only a 2 bar, then the solar field will have to unnecessarily produce all the steam at 10 bar, whereas a more viable way to do this would be just to give it to a process that requires its 2 bar. It's far more easier to produce steam from solar using 2 bar rather than 10 bar. So that is why I've differentiated both of them. Let's look at, I'll take an example. This is not an ideal example, but it will illustrate very well as to how do we go about evaluating different processes that are suitable and what should be taken on priority. So this is a typical sugar manufacturing process. If you look at it, we could take any process but apply the same principles. It can be dairy, it can be some other food processing, doesn't matter. So a typical process is that we use bagasse or coal to fire a boiler to produce steam, and then the steam, typically in a sugar plant these days, is also used to produce electricity. And then there are different stages of the process of producing sugar. Starting from the cane, you extract the juice, clarify the juice, then there is evaporation, then there is crystallization, and then drying. There are different stages requiring different temperatures of steam or hot water. So now, if we enumerate what are the process temperatures. Okay, as I said, the boiler, live steam, which is from the boiler, the maximum temperature is about 360 degrees centigrade. The process return from the process comes at 128. So similarly, there are other temperatures. You will see that there is a great amount of variation in the temperatures that are required for different processes, both in the feed temperature as well as the return temperature. So based on this, we can grade what is the opportunity for us for to implement solar thermal. Okay. So if you see the highest potential opportunities would be the ones which require the lowest temperature. The reason is, and the reason why I'm pointing out this is, many times when we talk to industry, they do the reverse of it. They try to get the highest temperature possible, which is difficult, especially in current, conditions that are. If you see, I'm based out of Hyderabad, and there's been so much rain this season that It's been almost cloudy for last 3-4 months or so. So nothing can be produced in or steam at high temperature cannot be produced in this. So if there are opportunities, low temperature opportunities, those should be given priority and looked at first, because it's much easier to generate temperature less than 100 degrees centigrade. And these processes like sludge drying, bagasse drying, makeup water or sugar drying, in this particular case, should be looked at first to convert to still possible. We should look at that. And then finally, these temperatures above 180 degrees should be looked at, depending on the location. That's not suitable. Not every location is suitable for producing temperatures above 180 degrees or so, and that too consistently. See, we have done projects where we have touched even higher temperatures. I'll show you later that in certain projects, we've reached even temperatures higher than 600 degrees centigrade. But what matters in an industry is, can you deliver that temperature consistently day after day? So just because we have achieved a particular temperature in certain conditions doesn't mean that we can go ahead and use that as an example to implement that for industry. Because industry, every day, the production has to be there. They are looking at consistent and stable source of energy, because the process temperature remains the same. So unless you are able to give that, uh, even one shouldn't implement this. And this is where the challenge with solar thermal comes, because in the fossil fuel based systems, we are in control of what should be the input, whether it is coal or it is diesel or any other fuel. We have a stock of it and we control the feed rate. Therefore, we control the output. So if the output required is, let's say, 100 kilowatt of heating, or let's say 5 tons per hour of steam, we know how much fuel we have to give for that, and we can get that consistently. However, in case of solar, the challenge is that we are not in control of the input. Therefore, we cannot be in control of the output. So it is very essential to understand this when trying to design solar thermal systems for industries, because no matter what happens on the solar side, whether it's up, down, not there, whatever it is, the commitment is that one has to deliver the required temperature and pressures of, if it's steam or of hot water, to the process, because the product being manufactured cannot be spoiled. That is the mainstay of the business. So this is where the engineering skill to design these systems comes, because these have to be designed in such a way that they modulate to the changing input in the solar thermal system. So out of this, if you see, we will look at the first one of the applications of this, which is, let's say, bagasse drying. Bagasse in sugarcane industry, the bagasse is used as fuel. Now, the way it is used as fuel is, today they simply take the bagasse and burn it. So, and it already has a lot of moisture. So if we so the what is the opportunity here? The opportunity for here of us is to remove the moisture. So if you remove the moisture and make bagasse go from 50% moisture to 10% moisture, the calorific value of that bagasse increases dramatically. Of course, this leads to better boiler efficiency. Okay. So this is an opportunity that is there because it's a low temperature application, and from the table what we see, it is almost 100% increase in the calorific value. On the face of it, it looks very promising. So later in the presentation, I'll talk about how to evaluate this opportunity, this specific opportunity. Evaluate for such low temperature drying, we can use uh, such systems which are air dryers. This is a specialized tube where it is open on both ends. So air is taken from, this is an evacuated tube, air is taken from the bottom and hot air is given from the top, and there's a ducted network where hot air is delivered. Hot air can be generated. This particular project was done not for bagasse drying but for lignite drying. Similar, this thing where you reduce the moisture and increase the calorific value of the fuel. Okay, so this is such a system you can be used where air um, hot air is used at 70 degrees or 80 degrees or 90 degrees to dry the fuel, whichever is going to be used in the boiler. Okay. Uh, one can use this hot air in different types of dryer. In this case, one can use a rotary dryer, as can be seen here. In other
Sir,
cases, yes,
sorry,
sir.
just 1 minute. Sir, in the please previous slide, sir. Vacuum tube heater.
Yes, sir. This one?
Sir, here the vacuum tubes are another end is closed, one end is open. I have doubt how air will go inside and will get heat, because this is only diffusion only takes place, I think so. Is it
No, sir, that
effective?
is why I mentioned these tubes are different from your regular evacuated tubes. These are opened on both ends. These are specialized tubes that we get it manufactured by our
Sir, is it
suppliers.
available in the market? This both ends open.
It is not available in the market. We get it manufactured on special order
Okay.
because there is no demand for this, right? In the market, there is no demand for this.
Yes, sir. Okay.
So these are made only to order. So if you see the bottom plenum or the
Hmm.
box is the intake of the
Supply.
air, and hot
Yes.
air, it rises through that. So this is empty. There's no copper in that, nothing. And it becomes hot and goes to the top. From there, air is again sent.
Okay, sir. Fine, sir. Thank you.
So after that, the air is introduced into a dryer like this. Okay, if you see this large duct that is going on the left corner, you will see that the air is being introduced into the dryer.
Yes.
Okay,
Okay.
so this is one possible low temperature application that is possible, where a fuel can be dried or anything can be dried, sludge. Another low temperature application which I had mentioned here, if you notice here, sludge drying. Okay. Why is it important to dry the sludge? Many don't pay attention, but in the industries, but transporting of sludge is sometimes an expensive proposition for the industries, because depending on where you are and what kind of effluent you have, um, there are companies which come and take away sludge, right? Once you dry it, it doesn't dry in most cases, but you still have to take away this waste because more waste is coming because of the production. So where do you store? So there are companies which come and take away this waste and dump it in landfills or wherever they do it. So there are companies, there are you have to pay for the transport of it. So the transport costs anywhere between 5 rupees to 10 rupees depending on the kind of waste and the location that you are in. So if you are able to dry this much effectively, then the cost of transportation can be significantly reduced, because every month you have thousands of tons of this effluent that needs to be transported, and all that needs to be done is to be dried. So what you see here is a solar sludge dryer that we constructed. If you see the philosophy behind this is, it is not clear from the picture, but if you can see through those vents at the bottom, there are actually sludge pits. Before this was constructed, there were just 8 sludge pits open to the atmosphere, and there was open drying which was happening. Now, open drying the sludge will dry at natural rate of evaporation. Now, in order to increase the drying, it was nothing but accelerating evaporation, right? Now, to do that, so we looked at it and say, what are the factors that will improve the rate of drying? One is, if we increase the temperature of the air, then the saturation point of that air will increase, which means the same volume or the mass of air can now absorb more moisture. So air at 30 degrees has a certain saturation point that air can contain, let's say, absorb only, let's say, 10 grams of air, and it will reach its saturation point. But air at 55 degrees centigrade can probably take up 30 or 35 grams of moisture. Let's say, I mean, don't go by the number, but I'm just saying it increases exponentially. So the same mass of air now does 3 times more work. Okay, so that is why a greenhouse-like structure was built. Instead of using an external field like this, which would cost, we simply it increased the surface area of radiation capture. Earlier, the radiation that was falling on the pits was the only radiation it was getting. By constructing such a structure, you increase the total surface area that is available for capture of radiation. So amount of energy, total energy that is available also has increased now. The third thing that is important is, of course, the evaporation is a surface phenomenon. So as more and more air is provided on the surface, drier air, the more evaporation will happen, and that's why you will see there's a fan inside that is pushing the hot air from above, hot air from the top to the bed surfaces, which increases the rate of evaporation. So these 3 things helped us increase the rate of evaporation, and the drying time reduced from 10 days to 2 days. And the sludge was much more drier, so you reduce the cost of transportation significantly. Okay, so so in this case we have only used solar, but the heat can also be supplemented further by, let's say, we have not done this, we have given this design, but have not had an opportunity to implement it. We can, what do you call, depending on the type of sludge, we can embed pipes like radiant heating that I had shown in the previous presentation, in which we can circulate hot water, heat. Even from a cooling plant, going to a cooling tower, it can come here and provide that heat and cool down and go back. It can use heat pump or even solar, additional solar collector field. It depends. In most cases, we try to use the waste heat that is available to enhance the evaporation rate in a sludge dryer. These sludge dryers are not common here, but are quite common in Europe, where there are automated sludge dryers, which you see, which can level and mix the sludge so that the drying happens here. The reason why it is popular there is because they have a problem of insufficient radiation, and therefore they use such greenhouses for faster drying. So this is another low temperature application that is feasible for industries. This many are available, aware, agri drying. I'll not spend much time. These are simple solar water heaters that were modified a bit to provide boiler make-up water preheating. As this is viable, especially if the fuel being used is not coal and something like a diesel, and there is a constraint of the space available, then feed water preheating will give the would be the application that would be most economically viable, because you will not require a large field, but at the same time there will be savings on the fuel. So all these are temperatures, applications that I've shown are temperatures which are below, most cases 70 degrees till now. We can use these, what are these? Compound parabolic collectors in the manifold that you see here, the main header pipe, and such collectors. This is installed in a automotive plant in Jamshedpur, and these can provide temperatures up to 150-160 degrees centigrade, but we usually recommend it for temperatures between 70 to 120 degrees centigrade. So if you see, this is the temperature profile of the output that we get from this field. You will see the field starts delivering high temperature, and then of course there is a storage tank also that is provided in this particular project. So this is for washing of parts. In an automotive plant, you have parts which are coming in and which need to be washed before they can be assembled together. Today, the hot water required for this washing is somewhere around 70 to 80 degrees centigrade, and electrical heaters are being used. These are like our regular, they are just the bigger version of the regular washing machines that we use at home. And so instead of using, and electricity was being used, so instead of using electricity, it has been augmented by water, hot water from solar. So you will see that even at 10 o'clock in the night, the temperature that is available in the tank is around 70 degrees. This has been done with a storage tank of about 2 cubic meter or so. This is something that I already talked about in my previous presentation, where space heating applications in very harsh conditions can be taken up using solar collectors and storing that heat in the tank. For higher temperature applications and for steam generation, we can start, we use parabolic troughs. So this is a small sized parabolic trough that we have installed for cooking, for steam cooking at a school, at a blind school in Hyderabad. Parabolic troughs usually are of much bigger size. I'll show that also. We manufacture that also. But this particular size has been designed because it was to be installed on a roof. The regular and the roof that we had available didn't. The building was old, so we couldn't manufacture the full scale parabolic trough. So a small scale parabolic trough. This is about 18 square meter. Each parabolic trough was manufactured. So this can produce temperatures up to 180 degrees, 200 degrees centigrade. But the application for here, again, there was storage, but the steam temperature that was required is about 120 degrees, 2 bar roughly. This is a full-scale parabolic trough. Each trough is 72 square meters. So this one is what you will actually in so there are installations except large installations that you will see in. So I'll just quickly show maybe a large installation of such thing. So this is multiple of such one parabolic trough that I showed. This solar field for power generation is in Gujarat. It's called Godavari Green for Energy. Not one of the, I mean, yeah, it is one of the first, not the first, but one of the first solar thermal based power generation plants. So what we manufacture for industrial applications is also of the same size. So if you see, the span is usually about, this is a standard design across the world. All of us get the same curve because the manufacturers have standardized the curve. So this is about 5.7 meters in the span, and the length works out to almost 12 meters. Yeah, around 12 meters. So that's a standard size everybody uses. Sorry, yeah. Lastly, for temperatures higher than that, for temperatures higher than 300 or 350 degrees centigrade, we have typically used heliostats. These heliostats, these are the heliostats that I was saying we could achieve around 600 degrees centigrade, but these we have not used in any industrial application so far. These are manufactured only for R&D purpose, and under certain conditions we have achieved above 600 degrees centigrade, used primarily for hydrogen production related application, but that is not a mainstream application. So hopefully these high temperature solar concentrators will also become viable. At this point, we don't see a viability for industrial applications. Hope it will require a little more work till we make it viable for industrial applications. So I will get into economics, but if there are any questions at this point, I'll handle that. Otherwise, I'll get into the economics of all these different type of concentrators.
Sir, I would like to know about the general procedure of the maintenance in this type of the plants. What is the maintenance requirement? What type of maintenance is required, sir?
the most, what do you call, the maintenance that is required in cases, whether cleaning that is required, okay, which is more stringent in these two types of concentrators, because they are very precise and concentration ratio is very high, and accumulation of dust significantly reduces their performance. But on such solar collectors, okay, you can see actually there is a little bit of dust. If there is a little bit of dust, there will be some amount of reduction in its performance.
जी
So
sir.
usually what we suggest for such collectors is cleaning it once in a month is sufficient.
जी sir.
But for these type of collectors, uh, the cleaning is almost daily, on a daily
Right sir.
basis.
Right
So
sir.
these
Thank
require more water. But
yeah.
more than that, apart from that, the maintenance, occasional maintenance that is required in these kind of ones are, if you can see, there is a slew drive here. There
जी
are drives because these are tracking systems, right?
जी sir.
These drives may need to be checked.
Right
Uh,
sir.
so, oops, sorry.
Yeah. Yeah. No, it's okay, sir. Thanks a lot, boss. I got it. Yeah, that's true.
Yeah,
Thank you very much, sir.
you're welcome. So let's look at the economics of this. Typically, greenhouse-based drying, which are much simpler, which I showed you for sludge drying and all, they will vary between 2,000 rupees to 10,000 rupees per square meter, depending on whether you're using polycarbonate, what kind of polycarbonate, or polyethylene film. Depending on that, it will vary in this range. ETC or CPC solar collectors will range from 12,000 to 22,000 per square meter. Parabolic concentrators 20 to 20,000 per. This is general range of price that you will have to pay for these collectors. The viability will depend on various factors. So let me take different scenarios to explain how the viability varies depending on the usage. And so the first one we'll take is, let's say, is it feasible to dry sugarcane bagasse economically using solar, right? So if we look at the sugarcane bagasse, the calorific value, the boiler efficiency, what we can calculate is, and the cost of bagasse, that bagasse for every 1 rupee spent delivers 605 kilocalories of energy. Okay, that is what I can get from 1 rupee I spent. Now let's look at the solar option. What we have to understand here is that the sugarcane business is seasonal. The bagasse is available seasonally, so it is not available. The operation is not to all 200 days. So the operation is only for 365 days. It is only for 200 days. So whatever advantage solar can provide, it can provide only for 200 days. Therefore, if we just take per square meter, solar can deliver 2000, little over 2000 kilocalories on a daily basis. That is the energy it can provide. Now, if we calculate the total energy this way, that solar can provide for 5 years, and if we take the cost of the installed system as 15,000, Then what we are looking at is calculation. We have to spend 1,000 rupees. So if we divide that, we will get that for every 1 rupee we spend on solar system, we are getting 143 kilocalories. Whereas every 1 rupee I spent on bagasse, I'm getting 605 kilocalories. So clearly, I am getting much lesser energy by spending on solar than I can get from bagasse. So this is not a viable replacement for bagasse in using in a sugar industry. Okay. So let's look at another example. In this case, this is we are looking at, if we are looking at somebody who's using diesel. Diesel's calorific value is 10,500 kilocal kg. So taking density and everything into account, finally we see that we are spending, by spending 1 rupee, we are getting 102 kilocals as far as diesel is concerned. That's the energy we get. And if this is an industry that runs, let's say, a food processing industry. So if it is running 365 days, at least 300 days out of that, if we assume that we can get solar energy, now what it will give is that, I think this 143 is wrong. We will be able to get 129 kilocals per 1 rupee spent of solar. This 143 here is wrong, sorry. So even though the cost of system is high here, even if we are spending a higher cost system of 25,000 rupees, it is viable in this case because they are using diesel, and with diesel they are only getting 102 kilocalories for every rupee spent, whereas investing in solar, even at a higher cost of 25,000 rupees per square meter, we will be able to see that it is viable. The viability of solar in an industry depends on different factors, and all of them have to be taken into account to determine what is the viability. So this is the answer. If there are any questions, I'll answer them.
Okay. Participants, is there any questions? Sir, first of all, let me thank for your elaborative discussion on industrial applications such as air heating in power plants and hot water heating for process heating, steam cooking, and solar drying, including economics. And you also elaborated various types of solar collecting system, including the focusing type and non-focusing type. It's very informative and useful information to all participants. The fact the discussion on this industrial applications in the field of solar thermal energy. Hello?
Yeah.
Dear participants, otherwise you may text your questions so that I will convey.
Sure. Sure, sir. That sounds good. Okay, sir. Thank you very much for the opportunity. I hope everyone has learned something from what I have shared. And there are further questions, yes, they can be. I can be reached through by sending questions to Dr. Srinivas, and he'll direct them to me.
Thank you, sir, for sharing
Thank
a great,
you.
some really nice experience to us.
Thank you very much. Take care. Yeah.
Okay,
Bye.
sir. Thank you. Thank you, sir.
All right.
Dear all, the next lecture today, the third lecture, we are starting around 2:30 after lunch. Please join this lecture, third lecture, at around 2:30 p.m. The lecture is by Dr. Ishwar Murthy, Sri Mata Vaishno Devi University, Jammu, on micro power systems, especially using thermoelectric effect. He is going to give a lecture on solar thermal applications. Thank you. Bye.